In this video, we'll start to learn the basics of stereochemistry. Before we start stereochemistry, we want to overview isomers and isomerism. So isomers are compounds that are constructed from the same atoms. If we remember, we have our isomers, we had our constitutional isomers, where they have the same formula but different connections. That would be if we had our butane versus our butane. They have the same formula, but the atoms are just connected differently. Stereoisomers have the same formula and are connected the same, but have different spatial arrangements of those atoms. We started seeing this when we looked at rings. And remember, when we had our rings, we had our top side of the ring versus the bottom side. Where our two groups were either on the same side of the ring or on opposite sides. That would be considered a stereoisomer. So as I just showed you, one of the stereoisomers we've already seen is called the cis-trans isomer or geometric isomer. And when we look at our cis-trans isomers, if we look at an example, I can say I have two carboxylic acid groups coming off of my alkene. They can either be trans or on opposite sides, or cis where they're on the same side. And these two groups do not convert between each other because of that double bond. So much so that they even have different names. The one that's trans, it's called fumaric acid. And the one that's cis, it's called maleic acid. And being in different conformations, cis and trans, gives them different physical properties. The trans one has a melting point of 287 degrees Celsius. Cis ends up with a melting point of 138. Big difference just by being cis and trans. Even more important is the cis one is considered an essential metabolite. The other one, the cis one, is actually considered a toxic irritant. So that'd be the big difference between cis and trans. They have very different properties. One's an essential metabolite, one's a toxic irritant. That's how little they interconvert between each other. You don't see a conversion between cis and trans around the double bond here. Instead, they have very different melting points, very different physical properties, are used by the body very differently. That was our example we've seen before about stereoisomers. So far, we've really just looked at the cis and trans. Now we're going to start looking at the three-dimensional shape. And with stereoisomers, what that is it's the study of the three-dimensional structure of molecules. So our stereoisomers are molecules that have the same bonding sequence, so they're connected the same. The atoms are connected to the same types of atoms, but it's a different orientation in their space. So if we look at three different ones, here we have CH3X. The only difference is that X. I can make them look like each other. There's no difference between these two. Same thing with CH2XY. So if we added a different type of substituent here, even still, I can make these two look identical to each other. I'll just need to rotate the bottom here a little bit and just move the Y from this side of it over to this side. But once we change that third hydrogen into another substituent, a different kind, we end up with a formula of CHXYZ. So we have four different things attached to that carbon. Now, if you try to make these two look the same as each other, you won't be able to. They have different three-dimensional structures. That's what we're looking at when we look at stereochemistry. And having those four different groups gives us a carbon that we consider chiral. And chiral molecules, chiral atoms, are objects that have a handedness. So that means that it's almost like if you look at your two hands, they are different from each other. You can't overlap them. If you hold your two hands next to each other, you can't make them overlap and identical. Your two hands are what we consider a non-superimposable substance. So that means it's not identical to its mirror image. A superimposable substance is where an object and its mirror image are identical. We consider those achiral. So if you can take the top, if you're looking at the top of your hands and you try to overlap them, you can't make them overlap properly. They're never going to completely cover the same fingers. But if you take your two palms, face them towards each other, it's almost like they're looking in a mirror. That's what we mean by a mirror image. So if you take the two palms, connect them together in front of you, you can get all your fingers, your two thumbs to connect, indexes, middle fingers, ring fingers, and pinkies all can connect together. But if you're just looking straight down from the top, those two hands, they don't connect. You can't get your thumb, your index, and your ring fingers to all connect together. Carbon atoms with four different substituents have the same type of handedness. They have the same differences in their three-dimensional structure, just like your two hands. So when you have four different substituents or four different ligands, they can have a spatial arrangement that's not superimposable. So if I have a mirror here, it's like the molecule's looking in a mirror. It's trying to get ready in the morning, it's looking in a mirror. But that tetrahedral carbon in the middle, it's not superimposable with that mirror image. I can't make them overlap with each other. And so that tetrahedral carbon in the middle, we consider that a chiral center or the chirality center. It comes with a lot of different names. It's either called the chirality center, chiral center, stereocenter, stereogenic center, asymmetric center, asymmetric carbon. We call it a lot of different names, but it's all to indicate that this carbon has stereochemistry associated with it. And to designate it has stereochemistry associated with it, as you just saw, you draw an asterisk. That says that carbon has a three-dimensional shape to it that can't be superimposable with its mirror image. So you can look for four different groups bonded to a carbon and designate it a stereocenter. This can either be a carbon by itself, like here, or it could be in a larger molecule. You can have more than one stereocenter in the molecule. So you want to look at every single carbon. If there's four different things attached to it, that's considered a stereocenter. So here we see we have a methyl group, a hydrogen, this side of the ring, which is the CH2, CH2. This side of the ring is a CH2, CHOH. That's how these two are different, because of that OH on this side. So that gives that chirality. This one, we can see we have an OH, an H, a CH, CC, and a CH2. That gives it chirality. Can do the same thing here. But if we look at, let's say, this carbon, here I have two methyl groups, no chirality. They have to be four different groups, always four different groups. So a couple general rules before we get too much further. Number one, if a molecule has no asymmetric carbons, so if it has no chiral carbons, it's usually achiral. So if there's no stereogenic carbons, there's no chirality. Simple as that. Number two, if a molecule has one asymmetric carbon, It has to be chiral. It must be chiral. So if I have just one asymmetric carbon there, the entire molecule becomes chiral. Number 3, if it has more than one asymmetric carbon, the entire molecule may or may not be chiral. Confusing, right? If we have more than one, sometimes you can still have what we call a mirror plane through the molecule. So let's say if we look at our compound here, we have 2 CH3 groups. So you can see each one of these is a chiral center. But if we look at this molecule and I draw a line right down the middle, doesn't this half of the molecule look exactly like that half of the molecule? If the two halves look the exact same when you draw a line down the middle, that's what we call a meso compound, which means even though it has chiral centers, it's not a chiral molecule. It's an achiral molecule. So if you can find a mirror plane, or if there is a mirror plane, inside the molecule, the molecule becomes achiral. So if you can find that mirror plane, your molecule can become achiral. And it becomes what we call a meso compound. So that's one to watch out for when we're looking at these rules and figuring out whether molecules chiral or achiral. Look for that mirror plane. So now looking at our chiral molecules. 2 chiral molecules that are mirror images of each other are called enantiomers. So enantiomers are chiral molecules that are mirror images of each other. And those are non-superimposable mirror images. So remember, they're non-superimposable mirror images. We call them enantiomers. And if you remember, our superimposable compounds, they can be placed on top of each other, and their 3D positions will start to coincide. But the enantiomers are non-superimposable mirror images of each other. So that would be an example if we had these, you can see they're mirror images, but they're non-superimposable mirror images. So therefore, I can call them enantiomers of each other. Okay, so now we've learned a little bit about the different definitions and different terms for stereochemistry. We learned about cis-trans, and then we started learning about our stereoisomers, including chiral centers, chirality, and a couple of rules. Next, we're going to start looking at how we can start to distinguish and identify these different enantiomers from each other and how to name them.